Thank you, Mr. Presley. So today I'd like to talk to you about decomposition of plants and algae in shallow lakes and how this leads to carbon burial. So shallow lakes are no more than 4 meters deep, and given the shallow depth, light is able to reach through the entire water column and support a very large community of primary producers. Now, since these lakes are able to produce so many primary producers or support them, when they die, if they're not fully decomposed, then there's more carbon available for a carbon accumulation or carbon burial in the sediment. Now, it's also important to remember that primary producers are not the only source of carbon for these lakes. Carbon inputs from the terrestrial sources are very important to carbon burial in these lakes, such as runoff or leaf litter during the fall. And this is because of the very large ratio of perimeter to volume in these lakes. So it's important to remember that the two carbon sources are primary producers as well as terrestrial. Now what we see here on the x-axis is lake area increasing in that direction, and this is carbon burial increasing upwards. And what we see in the relationship is that with a higher lake area, there's less carbon burial, whereas with a smaller lake area, there's a lot more carbon burial. And the lakes that we look at are right within this small lake area range, and as you can see, there's a lot of carbon burial in these shallow lakes. And what we can also see is that there's a very high variability in carbon burial. And our question is, what's driving this variability of carbon burial in shallow lakes? Now, shallow lakes also come in two different regimes. There's the clear regime, and then there's the turbid regime. Now, in the clear lakes, macrophytes are the most dominant primary producers, while in the turbid lakes, algae are the most dominant primary producers. Now, these different primary producer dominances also lead to very different environments in these two lakes. In the clear lake regime, the macrophytes take up a lot of the water column and therefore inhibit a lot of mixing in these lakes. So we'll find oftentimes stratification, a lot lower temperatures, and a lot lower dissolved oxygen measurings near the sediment at the bottom of the lake where decomposition is occurring. Whereas in turbid lakes, algae does not inhibit mixing of the water column. So we'll often find that temperature and dissolved oxygen levels are the same throughout the entire water column. Now, the rate of decomposition ultimately determines how much carbon is going to be available for accumulation in the sediment. And the two primary producers in these lakes are very different in their composition. Macrophytes are much more complex. They can contain a lot more cellulose than algae do, and therefore ultimately decompose a lot slower than algae do. While algae are very simple organisms, they're very easy to decompose. And in these two different regimes, there's also a very big difference in lake environments. And our question is, how do these different environments impact decomposition, and ultimately, how do they impact carbon burial? So, we used 1 millimeter mesh bags, and we stuck them with 4 different kinds of species. We used sago as our macrophyte, Chara as a macroalgae, Cladophora as a filamentous algae, and grass as our terrestrial plant. We could not use regular algae because there's no way we could fit it in our 1 millimeter mesh bags and ultimately represent decomposition accurately. So we had to go with the macroalgae and filamentous algae. And then we also used 2 different locations in each of our 11 lakes. We used a shallow location, which is about 0.75 meters deep, as well as a deep location that was about 1.25 meters deep. Now, we estimated the start dry weight by using wet-dry ratios, and then in the end we estimated the dry weight by drying our samples after we collected them. And here's an example. This is how our experiment is set up in our lakes. We have a buoy connected to the brick, and then from that buoy, we have a line that hangs, and connected to this line are all of our specimens, all of our species samples. And it's important to note that they lay stationary on the bottom of the lake. They lay in the sediment, so decomposition occurs naturally, as it would naturally. Now, we collected our samples at these different days, but today I'm going to be presenting you all the data from our collection after 293 days of decomposition. And then we also analyzed all these samples for dry mass remaining as well as for carbon content. However, all we have right now is the dry mass remaining data, so that's what I'll be presenting to you today. We still have yet to analyze the carbon data. And to analyze our data, we use the SAS program to compute a three-way ANOVA with our characteristics being species, depth, and lake. And then we also looked at different environmental factors that may play a role in decomposition, and those factors included temperature, dissolved oxygen, and pH. Now, we took these readings at 5 different locations across our 11 lakes to look at the ultimate overall lake impact, overall lake environment, and we measured these across the months of April and September. Now the question is, what did we find? Well, we found a significant difference in decomposition across the species, as you can see from our p-value. Here on the x-axis are different species that we use, and on the y-axis is percent weight remaining. So what we see is that Chara, our macroalgae, decomposed the fastest with the least percent remaining, followed by Cladophora, our filamentous algae, followed by our terrestrial grass, and then ultimately our macrophyte, sago. Now, what I'd like to point out to you is how interesting it is that Chara actually decomposed much faster than our filamentous algae. Our explanation for this is that Chara is much more brittle, so when we were collecting it at the 293 days or throughout, a lot of the pieces that were remaining after decomposition were very, very tiny. They were much smaller than the 1 millimeter mesh, so they just kind of washed out. Whereas Cladophora, although it's smaller in, like each filament is much smaller, it's very, very compactable, like you can make like a ball out of it. So that's our explanation for that difference in decomposition rates. And it's also very interesting to see that terrestrial grass decomposed a lot faster than our macrophyte. We did not expect this, since being terrestrial, it has a lot higher cellulose content than the macrophyte. But our explanation for this is we've been analyzing these for bug communities, and so far we've observed that there are a lot greater bug communities in our grass samples. There are a lot more chironomids, which push decomposition, which are involved greatly in decomposition. We find a lot more of them in our grass samples than our sago samples, so that could also ultimately lead to greater decomposition of our grass samples than our sago. Now, we did find a significant difference between the two different depths. We found that the deep location decomposed a lot faster than the shallow location. Again, this was very surprising to us. We anticipated that the shallow would decompose a lot slower, the shallow would decompose a lot quicker than the deep specimens. However, since this did not occur, our explanation for this is that maybe the bug communities in the deep location are ultimately driving the deep location species to decompose a lot faster. And again, we're still analyzing that data, so that's just what we propose at the moment. Now across our 11 lakes, we also saw a very significant difference in decomposition. However, we did not find a significant difference in decomposition between the two regimes. As you can see here, the blue bars represent the clear lakes, which are spread across our graph here, while the green bars represent the turbid lakes. So our question is, what is driving this variability? Because it's significant. Is it an environmental factor? And so that's what we looked at next. The first environmental factor we looked at was temperature. And what we expected was that with greater temperature, there would be more decomposition and less plant mass remaining. So what we expected was a negative relationship. However, we did not find a negative relationship, nor did we find any significant relationship at all, as you can see from our P and our square values. Next, we looked at dissolved oxygen. What we expected was that with higher dissolved oxygen levels, there would be more decomposition. However, we did not find that relationship, and we also did not find any significant relationship at all. Next, we looked at pH. Now, what we expected was that at a more moderate pH, there would be greater decomposition, since bacteria communities and invertebrate communities prefer a more moderate pH to live in, and therefore there would be more decomposition, more carbon burial, or less carbon burial at a more moderate pH. So what we expected was to see a relationship that looked something like that. However, we did not see that, nor did we see any significant relationship at all. So to recap, we did find a significant difference in decomposition across our different species. We found that Para decomposed the fastest, followed by our filamentous algae, our terrestrial grass, and then our macrophyte. We also found a significant difference in decomposition between the two depth locations that we used, and we found that the deep location decomposed a lot faster than the shallow location. And we also found a significant difference in decomposition across our 11 lakes. However, we did not find a significant relationship between decomposition in clear lakes versus turbid lakes. So our question is, what is driving this variability? Clearly, we have not found the environmental factor or the relationship yet, but we're still analyzing our data. Like I said, we're still looking at our bug communities. So hopefully we can find what is driving this variability, what is causing decomposition to occur more quickly, and ultimately what environment of a lake will cause more, or will lead to more carbon being available for more carbon burial. Now I would like to thank the National Science Foundation for the grant that they provided us, as well as the University of St. Thomas and the St. Paul Convention Center. Thank you.